Hello everyone, and welcome back to Nuclear Reactor Theory Lectures. Today we're going to discuss the most infamous and deadliest nuclear power accident in history, the 1986 Chernobyl disaster. I found that when non-nuclear engineers ask me questions about nuclear power, some of their most common questions are about Chernobyl. Chernobyl was pretty much the absolute worst-case accident that a nuclear power plant could expect to ever experience, and so it is important to understand why the accident took place and why similar accidents are impossible in modern nuclear power plants. In this lecture, we will discuss the Chernobyl accident through the lens of a reactor physicist, relying on many of the topics that we learned in this course. But it's important to also see Chernobyl through the eyes of a non-nuclear engineer. The Chernobyl disaster was a terrifying event, but it's perhaps even more terrifying to someone who doesn't know what's going on, or to someone who's afraid that the nuclear power plant next to their house will become the next Chernobyl. I ask you all to reflect on the material that you learned this lecture and that you have learned in this course, so that you can answer questions that your friends and family might ask about nuclear power in a way that is both patient, empathetic, and approachable. The Chernobyl disaster took place on Saturday, April 26th, 1986, and it involved the Unit 4 reactor of the Chernobyl nuclear power plant. The Chernobyl nuclear power plant contained two 1,000 megawatt electric first-generation RBMK 1000 reactors, Units 1 and 2, and two second-generation RBMK 1000 reactors, Units 3 and 4. The Unit 4 reactor is a reactor where the accident took place. The site also had plans to add on two additional RBMKs, Units 5 and 6, which were under construction at the time of the accident. These RBMK reactors are a peculiar design. RBMK translates roughly to a high-power channel-type reactor, and these reactors were intended for both power production and for producing weapons-grade plutonium. This diagram depicts a rough layout of the RBMK design. Unlike conventional light water reactors, where nuclear fuel is fabricated into fuel rods that are clad with zirconium and submerged in water, RBMKs are pressure tube designs. There is no rule that nuclear fuel needs to be submerged in moderator or coolant, like it is in boiling water reactors and pressurized water reactors, and pressure tube reactors are designed to remove heat from nuclear fuel by flowing pressurized coolant through the pipes that touch solid chunks of fuel. This pressure tube design has several advantages and several significant disadvantages. The first advantage is that keeping the coolant separated from nuclear fuel and fission products makes coolant chemistry and purity less of an issue. Fission products aren't going to flood into the coolant if the fuel cladding fails, and so concerns about water chemistry and crud buildup are much easier to mitigate than in conventional light water reactors. Another key advantage of pressure tube reactor designs lies in their ability to refuel the reactor and to shuffle fuel without actually shutting down the reactor. This design feature is known as online refueling. PWRs and BWRs are not capable of online refueling, which means that they must completely shut down the reactor and remove the top or the head of the reactor's pressure vessel to add or remove fuel. Conventional PWRs refuel once every 18 to 24 months, and this process takes about 43 days on average. Refueling is inconvenient and expensive. Shutting down a reactor for a full month means that the plant is making no money for that entire month, and even worse, that the electric utility that owns the reactor is on the hook to replace this power, which they do using more expensive sources. Reactors that are capable of online refueling don't have this problem. They can refuel without shutting down the reactor, and thus without disrupting the plant's mission. These photos, taken by Carl Willis, one of the many outstanding lecturers at the University of New Mexico's Nuclear Engineering Department, show the Unit 2 RBMK reactor from the actual Chernobyl nuclear power plant. In addition to being a nuclear engineer, Carl is a nuclear tourist, and he has visited the Chernobyl site roughly 7 times. Carl has generously given me permission to use photos from his Chernobyl visits in this lecture. As you can see from Carl's photo of Chernobyl Unit 2, The fuel elements in an RBMK resemble big, square Lego blocks. There's all sorts of structure to these fuel elements hiding underneath their square tops, but the modular design of these fuel elements, combined with the use of a pressure tube reactor design, allows RBMKs to shuffle fuel elements around the core, or to remove them entirely without shutting down the reactor. The goal of online refueling in RBMKs was not just to improve the economics of the plant, but actually to produce weapons-grade plutonium. Producing or breeding plutonium involves irradiating uranium-238 with neutrons, causing it to become uranium-239, which decays into neptunium-239, and eventually into plutonium-239. However, if you expose uranium-238 to a neutron flux for too long, then some of the plutonium-239 will absorb another neutron and become plutonium-240, which makes plutonium behave poorly in weapons designs. Therefore, reactors with online fueling are ideal for producing weapons-grade plutonium. They can just blast uranium-238 with some neutrons and remove it from the core without shutting down the reactor before it absorbs too many neutrons and accumulates too much plutonium-240. Weapons-grade plutonium production reactors in the US, such as the Hanford reactor, operated on similar principles. So why does online refueling make a reactor dangerous? Well, it doesn't on its own, but RBMKs had several other interesting design features. First, as you might have noticed here, the RBMK core had no containment building. Containment buildings are highly effective at both protecting nuclear reactors from the outside world, just like how my unhealthy obsession with bad movies protects me from unwanted social interactions, and containment buildings also serve to prevent the spread of radioactive material during any kind of accident. The TMI reactor accident released no radioactivity because it was all contained within the containment building. Yes, the site released some small amount of radioactivity after the accident when they evaporated away a pool of coolant containing radioactive xenon and iodine, but this release of radioactivity was done at a slow, safe rate in accordance with the site's license. The Chernobyl reactors had no containment, which is now an alien concept among modern reactor designs. Adding a containment building around these reactors would have more than doubled their construction time, which was a total non-starter for the Soviet Union. They were at war, and their goal was to win the nuclear arms race. So building containment buildings around these reactors was an unnecessary delay. However, these reactors did have a 1,000-ton biological shield, which was meant to minimize the dose in the reactor hull while the reactor was operating. Perhaps the most damning aspect of the RBMK design was how the design combined graphite moderator and water coolant. PWRs and BWRs use water as both the moderator and coolant, yet the RBMK used graphite as the neutron moderator and water as a coolant. RBMKs use graphite as their moderator because of what a great moderating material graphite is. As we discussed in the slowing down theory and lethargy lectures, the carbon in graphite is light enough to efficiently thermalize neutrons, but carbon's extremely small neutron absorption cross-section is so much smaller than hydrogen's absorption cross-section, which allows graphite to thermalize neutrons without absorbing practically any of them. In fact, graphite absorbs so few neutrons that a graphite moderated reactor can sustain a chain reaction using only natural enrichment uranium, which is exactly what the first man-made nuclear reactor, the Chicago Pile, used. So by using graphite moderator, RBMKs ran on 1.8% enriched uranium, compared to the higher 3 to 5% enrichment that PWRs and BWRs required. Using minimally enriched fuel made it much faster and easier for the Soviet Union to build RBMKs, which thus improved their position in the arms race. However, using both graphite for the moderator and water for the coolant in RBMKs meant that these reactors contained an enormous amount of neutron moderating material. They even had graphite on the tips of the reactor's control rods, which gave the reactor a little power boost whenever the control rods were withdrawn. RBMK designs contained so much moderating material that they operated in the dreaded over-moderated regime. In this regime, water coolant ceased to function as a moderator because they were basically oversaturated with moderator already, and instead, water acted as a neutron absorber or a poison. Removing any water coolant, be it by boiling it away or by breaking a coolant pipe, would actually increase the reactor's power, which is exactly what you don't want to have happen during a loss of coolant accident. So in technical terms, RBMKs had a positive void coefficient of reactivity. A sudden increase of power would cause a supercritical reactor to become even more supercritical. This positive feedback loop meant that RBMKs could experience runaway accidents, where the power increases until the reactor starts to physically disassemble. Positive reactivity coefficients are a reactor physicist's nightmare, and reactors in the US are not permitted to operate with positive reactivity coefficients. Just as we discussed in our kinetics lecture, there is a second feedback mechanism that acts in conjunction with moderator feedback. This is fuel temperature feedback. As fuel heats up, the neutron resonance absorption cross-sections undergo Doppler broadening, which results in wider, lower cross-sections that have the net effect of absorbing more neutrons. This slight change in the neutron's absorption cross-sections, which really isn't that slight since this is a log-scale plot, is a key safety mechanism for nuclear reactors, and it is enough to shut down most nuclear reactors if their power begins to increase too rapidly. Under normal operating conditions, RBMKs generated about 3,200 megawatts thermal of power, and had a fuel temperature reactivity coefficient that was just negative enough to outweigh the positive void reactivity coefficient, resulting in an overall negative reactivity feedback coefficient. However, as we discussed in my nuclear reactor kinetics and dynamics lectures, a reactor's stability can depend on its power. For RBMKs, both the fuel temperature and void reactivity coefficients became more positive as a reactor's power decreased, and the overall reactivity coefficient became positive when the reactors were operating below 20% of their full power. For the 3,200 megawatt reactors, this corresponded to a power of 640 megawatts. The RBMK operating manual forbade operating below 20% power for any sustained period of time. But remember this number, 640 megawatts, because it will appear again later in this lecture, and it will not bring good things with it. At 3,200 megawatts thermal, RBMKs were fairly large reactors. The first few generations of BWRs operated around 500 megawatts electric, and the very first generation of BWRs were around 100 to 200 megawatts. A 3,200 megawatt reactor is a large nuclear reactor, even by today's standards. The benefit to such a large reactor was both that these reactors could produce a lot of electricity, thus providing an important service to local communities and industry, but also that the high power meant that the reactor could breed weapons-grade plutonium at a faster rate. To generate this much power, RBMKs had to be physically large. Their large size meant that RBMKs had a dominance ratio that was very close to 1, and thus that different parts of the core were neutronically decoupled. This decoupling meant that RBMKs were subject to localized criticalities, which decreased their stability even further. To try and mitigate this instability, the Chernobyl Unit 4 reactor incorporated a supercomputer to detect unsafe conditions while the reactor was operating. This supercomputer is of course primitive compared to today's average off-the-shelf computers, but it was adequate for detecting localized criticalities and instabilities while the reactor was operating. So long story short, RBMKs are not what we think of as normal reactors. Perverse incentives cause these reactors to include multiple design features that made them riskier than other reactor designs. The PWRs and BWRs that we have in the States do not have positive void coefficients, and therefore it is not possible for one of them to experience a Chernobyl-like accident. So given all these perhaps unwise design features, how did the Chernobyl accident actually unfold? It may only have been a matter of time until an RBMK had a Chernobyl-like accident, but it turns out that the circumstances of the accident and the actions of the operators made the accident much, much worse. The Chernobyl accident was, ironically, the result of a safety test. Nuclear fuel continues to release energy after a nuclear reactor is shut down due to fission reactions that are induced by delayed neutrons, and also because of radioisotope decay in the fuel. This heat generation dies down rapidly after a reactor is shut down, but we still need to remove several percent of the reactor's power for an extended period of time. Otherwise, the fuel could melt and the clad could oxidize and release hydrogen gas, which is very explosive. Most reactors remove this heat by pumping coolant through the reactor, but these pumps require power to operate. If a natural disaster like an earthquake, a hurricane, or a tsunami causes a loss of off-site power, the nuclear power plants will rely on diesel generators to provide power for these pumps and to keep the fuel at a safe temperature. The Fukushima Daiichi accident happened because an enormous 15-meter tsunami knocked out the plant's off-site power and flooded the site's backup diesel generators. It's worth noting that a Fukushima-like accident could not happen in the United States because after 9/11, U.S. nuclear power plants started housing their steel generators in what are essentially hardened steel bunkers. Anyway, before I go off on a tangent and discuss a different nuclear reactor accident, let's get back to Chernobyl. Backup diesel generators in the US have a starting time of about 10 seconds, which is extremely responsive, but RBMK diesel generators took about 3 minutes to start up. Engineers at Chernobyl postulated that they could use inertia from turbine flywheels to power the coolant pumps for about 40 to 50 seconds after losing off-site power, and they sought to confirm this theory during the ill-fated safety test at Chernobyl Unit 4. Now, the original plan was to perform the safety test on Friday, April 25th. However, the May 1st Labor Day holiday was the following week, which meant that this was a holiday weekend. As such, the most qualified workers, the A team, were home enjoying the weekend with their families. That was okay though. The B team was capable of performing this test, but the problem was that they never got around to actually doing it. The test required operating the reactor at a power between 700 megawatts thermal and 1000 megawatts. But because of the holiday weekend, the power demand on the Chernobyl plant was much higher than usual. Lowering the reactor's power could mean leaving families in the dark while they celebrated the holiday weekend, and therefore, the Unit 4 operators decided to delay the test by about 9 hours. By 11:10 p.m. that night, the grid's electricity demand was low enough to start decreasing the reactor's power and to perform the test, but a shift change was scheduled shortly after midnight. This midnight crew, who I affectionately refer to as the C team, was not qualified nor intended to perform this safety test. Nonetheless, they had deadlines to hit, and the B team certainly wasn't going to stay around for a double shift on a holiday weekend, so the C team started performing the test. The Chernobyl plant's deputy chief engineer, Anatoly Dyatlov, was present to supervise the test, but his expertise alone was not enough to prevent the disaster. The Chernobyl Unit 4 control room looked a lot like this, which is actually a picture of the Chernobyl Unit 3 control room. From his view at the supervisor's desk, the Chernobyl Unit 4 control panel looked a lot like this. As they decreased the reactor's power towards the desired 700 to 1000 megawatt range for the test, the senior reactor operator, Leonid Toptunov, slipped and lowered the reactor's power too quickly. Leonid was 25 years old and had only worked as a senior operator for approximately 3 months. The reactor's power hit 720 megawatts, which was within the desired range, but it continued decreasing further because the operator had dropped the power so quickly as to cause a buildup of xenon-135. Xenon-135 is a fission product that has an enormous 3.5 million barn cross-section for absorbing thermal neutrons. Xenon-135 is produced naturally as fuel fissions, and it is gradually removed from reactors by either absorbing a neutron or by decaying, which it does according to its 9.2-hour half-life. Xenon-135 concentrations normally settle at an equilibrium level while a reactor operates. A power increase will produce more Xenon-135, but this Xenon-135 production rate increase is counteracted by an increase in the reactor's neutron flux, which causes Xenon-135 to absorb neutrons and to be destroyed, also at an increased rate. Since Xenon-135 is produced with a slight delay, a reactor that drops its power too quickly can stall out because of a buildup of Xenon-135. The Xenon-135 in the reactor is still being produced at the high, full power rate because the Xenon-135 precursors haven't had time to decay into xenon yet. But the rapid power drop means that Xenon-135 is being burned away at a lower rate by a low-power neutron flux. So when the Unit 4 operators slipped and lowered the reactor's power too quickly, the Unit 4 reactor started building up so much Xenon-135 that the reactor could not stay critical. The power dropped from 720 megawatts down to only 30 megawatts, which certainly was not enough power to perform the tests. In a scramble to raise the reactor's power, the operators began to withdraw control rods. The RBMK's design specifies that the reactor must always contain a minimum of 30 equivalent control rods, and the chief engineer's approval was necessary to operate at this minimum value. Under certain very special circumstances, this limit could be lowered even further to an absolute lowest minimum of 15 equivalent control rods. In an effort to overcome the Xenon-135 buildup, the Unit 4 operators had withdrawn so many control rods that the core only contained between 6 and 8 equivalent control rods. A full 193 of the reactor's 211 control rod elements were withdrawn from the core. Things get even worse from here. The maximum allowed coolant pump flow rate during the test was 7,000 cubic meters per hour, yet the reactor was operating at 8,000 cubic meters per hour. The operators increased the pump flow rate above this allowed limit because it allowed them to quickly repeat the test if necessary. Unfortunately for them, more coolant flow means less feedback, which magnifies the impact of any accident. Furthermore, the high coolant flow rate meant that the coolant in the core was essentially solid, meaning that the water in the core was almost entirely in liquid phase, and that none of it was boiling into vapor. The water was nearly at its saturation temperature for boiling, which meant that the water was ready to flash into steam if any more heat was added to the system. Having all of the coolant suddenly flash to steam is not good in a reactor with a positive void coefficient. Eventually, the reactor operators managed to stabilize the reactor, without control rods, at an operating power of 200 megawatts thermal. Do you remember that number from before, when we said that RBMKs were not permitted to operate below 20% of full power, or 640 megawatts? Well, operating at 200 megawatts meant that the Unit 4 reactor was operating in a highly unstable regime, and that it had an overall positive power feedback coefficient. The reactors also blocked the automatic turbine trip signal, thus removing one more shutdown safety mechanism from the reactor. They did this so that they could repeat the test quickly if needed. Now, the moment of truth. They began the test. Just before they began the test, the reactor's instability detecting safety supercomputer alerted the operators that they needed to scram the reactor now. So what did they do? They shut down the supercomputer. The operators then shut down the coolant pumps and began the test at 1:23 a.m. and 4 seconds. They noted that the reactor's power began to rise slowly, probably because Xenon-135 began to slowly decay away and burn off, and probably also because of feedback effects. With no heat removal, the reactor's temperature continued to rise. A few seconds later, at 1:23 and 31 seconds, the reactor's water coolant flashed to steam. Because of the positive void feedback coefficient, this inserted 1.7 dollars of positive reactivity. You'll remember from our kinetics lecture that $1 of reactivity is enormous. It's enough to bring a reactor prompt supercritical and cause a rapid, dramatic increase in the reactor's power. By 1:23 a.m. and 40 seconds, the reactor operators realized that something was very wrong, and they scrammed the reactor. The graphite-tipped control rods entered the reactor, but they only went 1/3 of the way into the core. This servo indicator from Unit 4's control panel shows where the control rods stopped. The control rods may have stopped because the graphite in the core had fractured and was blocking the control rod channels, or they may have stopped because the core was now molten. In either case, the graphite tips on the control rods were far enough into the core to insert another $0.50 of reactivity, which the already prompt supercritical reactor did not need. To make matters worse, the reactor's rapid power increase had burned off all the xenon-135 that had previously accumulated. This inserted several more dollars of reactivity. At 1:24 a.m. and 0 seconds, a steam explosion lifted the 1,000-ton concrete containment lid off the Unit 4 reactor. A second, even larger explosion occurred 2 to 3 seconds later, likely due to hydrogen that had been produced by oxidizing the fuel's zirconium clad. These explosions destroyed the reactor and the reactor hall, damaged the control room, and blew the 1,000-ton biological shield off the top of the reactor. Unit 4's final power reading before the explosions was 33,000 megawatts. Chernobyl aftermath. These explosions released roughly 4 billion joules of energy, which is equivalent to the energy released by about 10 tons of TNT. The explosions also ejected between 3.5 and 4% of the reactor's fuel from the reactor. The reactor was now so hot that the graphite moderator in it caught on fire, causing thermal updrafts that wafted radionuclides from Chernobyl's core up into the atmosphere. This graphite fire was eventually extinguished 4 hours later at 5 a.m. by firefighters using water, sand, clay, and boron, but not before 25% of the core's graphite had burned. The fire was so hot that the firefighters' boots were melting into the ground while they stood 50 meters away from the core. After the accident was over, the Soviet Army brought in 600,000 troops to help clean up the graphite and reactor debris. These troops were known as the liquidators, and they were used essentially as biological robots. Radiation fields around the fuel were so high that they would fry the electronics of any robot, and so the Soviet Army was forced to use humans to clean up the debris. Minimizing one's radiation dose is a game of maximizing the distance between you and the radiation source, maximizing the amount of shielding material between you and the source, and, perhaps most importantly, minimizing your exposure time. The liquidators used this principle to clean up Chernobyl. A soldier was given one quick task, such as quickly throwing a piece of reactor fuel into a wheelbarrow, and then their job was done. If they did their job quickly enough and ran away immediately afterwards, then they wouldn't get too high of a dose. After 600,000 soldiers each did their 1 or 2 quick tasks, the Chernobyl site was now cleaned up enough to be under control. Let's finish this lecture by discussing the human cost of the Chernobyl disaster. How many people died because of the accident? There were 57 deaths that were directly attributed to the Chernobyl accident. 2 workers died during the reactor's explosions, 4 died during a helicopter crash, 29 died from acute radiation syndrome, or radiation sickness, and 3 died from medical complications. Overall, there were 237 confirmed cases of acute radiation syndrome after the Chernobyl accident. The majority of these cases were not fatal. The long-term effects of radiation exposure are not terribly well understood, but studies have found no statistically significant increase in cancer rates among the liquidators who survived the Chernobyl cleanup. A study by Rahu in 2006 did find a statistically significant increase in thyroid and brain cancer rates among the liquidators, but this increase may be explained by the fact that these folks were actually screened for cancer. Many people have cancers that do not grow significantly and thus go undetected throughout their lives. So subjecting the liquidators to cancer screening could result in artificially inflated cancer rates because of these non-threatening cancers that were found. So what was the long-term effect of the radionuclides that Chernobyl's fire wafted up into the atmosphere? This is where things become less and less clear. Much of the dose dispersed from the Chernobyl accident was caused by radioactive iodine-131, cesium-134 and 137, and strontium-90. The radioactive iodine was highly volatile and was spread farthest from the reactor, thus making it perhaps the most concerning of the fission products released. Well, at least initially. Iodine-131 has an 8-day half-life, so the other, longer-lived radioisotopes eventually became responsible for more of the long-term dose. Because of challenges with data collection, methods for quantifying mortality, and the wide variance in cancer rates among different populations, it's extremely difficult to know how many cancer deaths Chernobyl caused. To go even further, it's extremely difficult to even know if Chernobyl caused a statistically significant increase in cancer rates. Radioactive iodine accumulates in the thyroid gland, where it can cause thyroid cancer. Thyroid cancer is both easily detectable, doctors can detect it simply by feeling someone's throat, and thankfully, thyroid cancer is also extremely curable. The iodine-131 released from the Chernobyl accident caused an estimated additional 6,000 cases of thyroid cancer, which led to a total of 15 deaths. The number of eventual non-thyroid cancer deaths caused by Chernobyl is highly debated. The International Atomic Energy Agency and a National Academy of Sciences Biological Effects of Ionizing Radiation report estimate an additional 4,000 cancer deaths due to Chernobyl. The Union of Concerned Scientists estimates an additional 27,000 deaths, and Greenpeace estimates somewhere between 93,000 and 200,000 excess cancer deaths. UCS and Greenpeace are anti-nuclear advocacy groups, so I personally do not really trust their estimates. Nonetheless, the true death toll from Chernobyl is somewhere within this range. It's somewhere between the 57 deaths that were directly tied to the accident, all the way up to several thousand and potentially tens or hundreds of thousands. This accident should have been preventable, and each one of these deaths is a tragedy. But does the Chernobyl accident mean that commercial nuclear power is too dangerous for humans to handle? In my opinion, no, not at all. As we discussed, the RBMK design had multiple risky design features that no modern nuclear power plant shares. Furthermore, the Unit 4 operators operated the reactor in a way that made the accident as bad as possible. Still, even if you ignore these mitigating factors, Chernobyl likely caused several thousand additional cancer deaths. Putting this into perspective, every year, pollution from coal power plants caused between 7,500 and 30,000 deaths in the US alone. Globally, it causes 4.3 million deaths. Stairs kill roughly 7,000 people every year. That's roughly 1 to 2 times the likely death toll from Chernobyl every year. Yet there are no anti-stair advocacy groups. In my opinion, the extreme circumstances that led to the Chernobyl accident should not discredit a technology that has a powerful potential for achieving energy independence, reducing our reliance on fossil fuels, and fighting climate change. If you're interested in learning more about acute radiation syndrome or the health effects of radiation, I discuss radiation biology in a fair bit of detail during one of my Nuclear Criticality Safety lectures. I've provided a link to this lecture in this video's description. I hope that you've enjoyed this lecture series that you've learned a lot about nuclear reactor theory. Please let me know if you have any questions, comments, or requests regarding these videos, and thanks for watching.